We explored multi-subtask policy learning in a robotic manipulation block stacking problem.
Robots have been widely used in industry for many decades, but it requires tedious task-specific programming and fine-tune. In this project, we experiment a fast learner agent with generative capability to make sequential decision under uncertainty. The agent will learn the subtask and also learn how to combine the capability for subtasks into more complex tasks. The most challenging for this project is the very huge state action space for the 7-degree freedom of robot. Next slide. Model-based policy use the autoencoder-decoder to convert high-dimension camera image into the low-dimension representation, and then training a deep dynamic model to do the predictive control. On this project, we are particularly interested to use the behavioral cloning and then DDPG. The latest DDPG, referring to diagram on the right side, called TD3, they utilize 2 target queue network and take a smaller target queue value and also apply the delayed policy update and also add noise to the action space. Next slide.
We use the Robotic simulator for our environment with Sawyer arm robot. The action space were the operational space controller with relative positions. The observation space are the robot configurations, which are the join and the positions. We also have the image 64 by 64 image, and we also have the object positions. For the reward, there are dance reward for motivating the robot to move and the sports reward for the whole task. Next slide. We consider 3 learning methods for our agent to learn. The behavior cloning, which maps between state and action, and the policy gradient method, which are PPO and TD3. We also consider splitting the task into 2 subtasks, the picking up the cube task and the placing the cube task. Next slide.
To generate data for behavioral cloning, we defined a scripted expert policy whose actions move the gripper towards predefined relative waypoints. We then generate 10,000 episodes of expert data with randomized block positions and uniform noise added to the actions. The expert policy first positions the arm in a prime waypoint above the red cube before descending for the pick operation. It then carries the cube to a prime waypoint above the green cube and places it down.
Here are the model architecture for our policy network. We put the image on the CNN stack and the observation on the dance stack. We concatenate them together and put them into the combined stack. Next slide.
The expert policy is extremely effective in stacking the cubes due to its knowledge of the absolute block positions. However, the clone policies are largely unsuccessful, both when trained on the full task data and data from the picking subtask only. The online methods, TD3 and PPO, have similarly poor performance after searching across several hyperparameters. The learned policies display a bias in the relative action command, causing the arm to dive towards the boundary of the workspace. We have successfully created an expert block stacking policy and are actively learning policies through behavior cloning, TD3, and PPO. Our next steps to improve performance are to allow direct observation of the cube positions for behavior cloning and to continue to sweep across hyperparameters for the online methods. The final step will be to combine the methods by using the cloned policy to initialize further online training.